Before I start, right here I'm going to add timestamps so you can kind of skip through and see the different sections of my video. Okay, so this is Sudoku, which is my project. So I'm just going to explain a little bit about how the game works and a little bit of the math behind it. So first I'm going to tell you how the game works. So I have 3 rules. So first you're going to notice, before we start with the rules, I'm going to show you this grid. So you'll notice there's a 9x9 grid, and actually it's made up of 9 separate grids. So you'll see there's 1, 2, 3, 4, 5, 6, 7, 8, 9 different 3x3 grids inside of it. So the way you play the game is that you're basically trying to put numbers in here in a way that there is, which follows these 3 rules. There can only be 1 number per square. Every column in a row must have 1 of every number, 1 through 9, and that means that no numbers can repeat in the columns. And then that follows the same with squares. Every square must have every number 1 through 9, and there cannot be any repeating numbers. So what I'm going to do here is kind of show you some of the basic strategies of how you play this game. So first we're going to look for a number, like let's find one here, number 8. So 8 here. No, never mind. So here, we found this right here. So the way you can visualize it is like this. So we're going to do this part here. So I know 3 goes here, but this is how I can prove it. So first, you're going to notice, so you have to remember these 3 different rules. So I would say that rule number 2 is the one that comes in handy the most, and that is that every row must have 1 through 9, no repeating. So if there's this thing right here, so we have these 3s right here, right? So you see this, so I'll show it on screen. So these 3s, they almost block out rows. So it's like this. So these 3 are completely off limits. And you've noticed that there's not a 3 in this box, so we know a 3 has to go in here somewhere. We just don't know where yet. So these 3 blocks out. This 3 blocks out these 2. This 3 blocks out this. They also block out these, but we're not too concerned with that yet. These rows, we're not concerned about that. So then, now, that means that these 3 are blocked off, so we have these 2 left. You're going to see we have a 3 right here. That means that there must be a 3 right here. And the reason that is because you see, if you notice this right here, this is going to block off this right here. So we have this one blocks off these 2, this 3 blocks off this one, this 3 blocks off this one. So we have, this is the only spot left that we know a 3 must go. So yeah, so you can keep playing the game a little bit more, and I'll actually time lapse it, and I'll show you as I play the different strategies that I use to show you how to solve the game. So here's another one here. So we have 1s right here, 1's right here, and a 1 right there, so we know 1 has to go there. So here's another one right here, which is a good example of rule number 3. In rule number 3, as I said before, is that each box must have every number 1 through 9 with no repeating. So right here, we might actually not know exactly what this number is and have any way to prove it except for this rule. So you'll see here, as we count up 1, 2, 3, 4, 5, 6, 7, 8, then we know, oh, there's got to be a 9 in there. So that would follow the 1 through 9 rule. And again, without that rule, we might not know, we might not say, only a 9 can go in that spot. We don't really know. Well, actually, we could, but anyway, doesn't matter. So I'll go back to the reason why I said that. Maybe I should explain that more. So we have here, right here we have a 9, right? And I said there's no way to prove it, but there actually is a way to prove it. Only a 9 could go there. So first what you're going to do is actually, there might not be something saying that points it out in your face, but it gives clues to show that there could not be a 9 there. So if we ignore rule number 3, which is that every box must have all the numbers 1 through 9. So you go here, so you're going to know, let's start from 1. A 1 can't go there because there's a 1 right here, right? So 1 cannot go there. 2, now we might not have a 2 here, so we'll skip it. We can just pretend that this 2 is blocked out there. 3 is also blocking that one off. A 4 is blocking that one off. 5 is also blocking that one off. 6 is blocking it. 7 is blocking it. 8 is blocking it. Well, if you can't have 1 through 8, you got to have 9, so that is kind of how that strategy works out. So there are actually a few algorithms you can use to solve Sudoku. For example, one is called the backtracking algorithm, which is definitely something you could actually use in math. I mean, it kind of depends on what scenario you'd be using it for, but one common example that I'm sure all of us have done is if you have if you have a problem, you have 4 answer choices, and you're not sure, instead of actually solving the problem, you plug in the answer choice to see if they work. So this is one way that a computer could solve for a Sudoku. So as an example, I have the equation y equals x, which is just this line right here. And the way I have it solved is that what this function is doing right here, which is not actually a function, you'd have to program this, but basically what it's doing is it has this little value here, so it has x is equal to n plus 1, y is equal to n plus 1. And then it's going to start at n is greater than or equal to negative 1. It's going to move from n is greater than or equal to negative 1. So basically, with a step size of 1. So that means that on the first step, if it's at negative 1, it'd be negative 1 plus 1, which is 0, and then 0, 0. So it's going to start at 0, 0. And I can't really describe this here, but we can pretend that it'll add 1 to the next n if, this should be it right here, let's say y. So we'll have our x's and y's. So we'll say that once it actually meets the graph, so for example, 0, 0, it's going to start with 0, 0, it's going to say, oh, well, 0, 0 works, so it's going to move to the next. So it's going to add 1 to the x. So then we'll see that 1, 0, there's no graph there, so it's actually going to move to the next one. And then it's going to go 1, 1. So once 1, 0 is unachieved, it's going to go up 1. It's going to start using y, going up y until it gets the correct value. So then at 1, 1, it finds the correct value, so we're going to start here. And then we're going to move up, and you can see what I'm saying here. So this is kind of a method you can use for Sudoku, is looking at one spot, like let's say this square here. You're going to start with 1. Say, oh, a 1 cannot go there. A 2. Oh, a 2 could go there, but obviously we're not exactly sure, so I'll put a note. 3, cannot be a 3 because there's a 3 in the box. 4 cannot be, so there's a 4 in the box. 5 cannot be right there. 6 cannot be. 7 cannot be. 8 cannot be. 9 cannot be. Then, oh, wait, look. Oh. And this was actually not even on purpose. A 2 must go there. So that is a mathematical explanation of how you might do that, and obviously some computers can actually solve that. So you can make a program on your computer that would actually solve for all the possible combinations of Sudoku, and this is one method you could use to do that. Okay, so here I'm using a program called PyCharm, which runs Python, which is a computer programming language that's super readable. That's why I chose it. So what this is doing is it's kind of doing what I talked about previously, and it's a script that is a brute force application. If we pretend that we have one line of a Sudoku puzzle, like shown in the above, what it actually is doing is it's going from left to right and showing and testing it, and it's saying if there's a 0 or if the number has already shown up, it's going to add 1 to the number until it finds a pattern that perfectly follows the 1 through 9, no repeating. And in this case, it's just 0, or it's just 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so now I'm going to explain the code in a way that makes a little bit more sense, and it all goes back to this equation that I'm at right here, which is basically brute forcing it. So it's saying I start here, and if it's a match, it adds. If it's a match, it adds an x. If it's not a match, it adds a y. And it's going to keep going until it gets all the matches like that. So here in the code, first what I'm doing is basically making a grid that's just zeros. So we're going to pretend that this is just a single line of a Sudoku, so you could pretend it like it's the top line of the Sudoku. And this is how a computer could possibly generate the first line. So it starts as all zeros, and as you know, 0 is not a valid number in a Sudoku problem, I guess you could say. It must be 1 through 9, not 0. So 0 is like a filler, basically. Is kind of don't really worry about it. So what this is doing is it's saying it's going to start here, and it's going to work its way through. So it's saying it's going to start at this one, and then once it runs this, it's going to go to the next one, next 0, it's going to run this. So this is basically saying that if it finds that this, so we'll start here. So so the first one it's going to run this thing right here. It's going to run the very first 0, and it's basically saying that if there is more than one of that number in this array, or the number is equal to 0, it's going to add 1. it's going to add 1 to this number. So instead of it being 0, it's going to be 1. And then it's going to repeat that for every single one of these until we get this right here. So what I can actually do is copy this and put it right here, and you'll see the process. So it's saying, this is actually kind of the timeline of how it follows. So first, it's 1 1 1 0 0. It's 1 0 0 0 1 2 1 2 1 3 3. And this is how a computer could actually generate something like this. Oh, I actually have this. That's the problem right there. Okay, so here is correct way. I accidentally deleted that. But this shows the process of how the computer is actually solving for it, and how this function is doing that. And this is a brute force application that follows this equation right here, which kind of shows the math behind how you could use some of the math you could use for Sudoku. So the question I'm sure a lot of people are asking is, how many solutions are there to Sudoku? And there actually is an answer, which is this number right here, 6.671, 10% to the 21st. However, the math behind it is actually very complicated, and that is because you can't just have a board, for example. You can't just say random numbers through 9, random numbers through 9, random numbers through 9, if that makes sense. You can't just say randomly pick a number for here, randomly pick a number for there. Even if it is all the numbers 1 through 9 correctly in the rows, the math that it takes to make sure that the rows and columns do not line up is actually very advanced. But it actually has been solved, and it was used, a computer was actually used to complete the calculations, and this is the number that it came up to, which is a lot of, like a very big number. But it kind of reminds me, and it kind of something that you should think about, is similar to like a Rubik's Cube, for example, which has 44 quintillion possible combinations. It's similar to that, because in a Rubik's Cube, every single side has a color, obviously, but you can rotate the side. You can rotate it on the x-axis, you can rotate it on the y-axis, you can rotate it on the z-axis. So it's kind of like this. I mean, there's so many different ways you can change the puzzle. But similar to a Rubik's Cube, the math is not that easy to solve, because, for example, let's say you have the top white piece of a Rubik's Cube. You can't also be calculating for that on the bottom of the Rubik's Cube. Like, there can only be one of each, which makes it really hard to solve the math. And what I mean by that is, for example, in one of these, it's very hard to figure out, oh, you can't, there has to be, it's easier to make, for example, the rows have all numbers 1 through 9. But it's going to be hard to make also the columns follow that same rule. Now, this algorithm does it, but it's very difficult to just basically, for example, what you could do is just tell this thing to go infinite times until there's no more matchups. And you'll realize that that's actually very rare, and that would take a massive computer and thousands of hours to do. So that's kind of something that the really advanced math goes into that. But it is interesting. It's something you should think about.